Are we recording? Okay. So this is now the first part, or as much as we can cover today, of 11.2. Did you guys all take AP Physics 1 last year? Are any of you in, oh, we don't even have Physics C in this year. Okay. So how much vectors did you learn about or did you work with last year? In calc a little bit. Okay. So I'm just going to assume that maybe we've forgotten, and I'm going to start, from the beginning, and I'll go as quickly as I can. If anything is new or I need to slow down, just let me know. Okay. So you did do a little bit of physics? Okay. So the thing is, between physics and math, the notation is probably going to be a little different. I would argue that it's more organized even. But so we're going to start from that. So let's say we have a vector. Okay, and by the way, what is a vector? It looks like a ray on paper, right? But it does actually end. So there's an initial point and a terminal point. Okay, and what makes something like this a vector is that we have a direction and there's a length to it. Those are the two things necessary. So just like if you're driving your car, right? 55 miles an hour by itself is just a speed, but you say 55 miles an hour headed east, now we're talking about a vector. Does that make sense? So that's the only thing that's different. Okay? Now the notation, there are several ways that you'll see things like this written out. One way is you actually write kind of like what you did in geometry. If this looks like a ray, you would write it in that symbol. Okay, but we interpret that as being a vector starting at P and ending at Q, instead of a ray starting at P going through Q. Okay, that's the only difference. You'll also see this symbol means the same thing, it's just two different ways of writing it. Okay? Now, you'll also see that sometimes if this is labeled with a smaller, like a lowercase letter, it'll be a bold lowercase letter in the book. Okay? So anything that's bold or written in this format with starting at P, ending at Q, you need to remember that that is a vector. Okay? And if that is the case, we could even say in this case now that A and this is for the book. When you write a single lowercase letter, I don't want you making it bold on paper. Just put a little vector symbol over it so we know we're talking about vector A. Vector A is the same as vector PQ in this case. And we need to know that the initial point is P and the terminal point, the ending point, is Q. Okay. This notation you guys seen this before? Okay. All it means is length or magnitude. The fancy word that we're going to use is norm. So if you're asked to find the norm of a vector, it really is just asking you to find how big or how long it is. Okay? Here's an example. Let's say we start with a point at 4, 5. Q, let's say that that's at -1, -1, and I ask you to find the magnitude of PQ. How would you do that? Just the distance formula, right? Imagine that, what we learned or reviewed yesterday. And by the way, these apply in 3 dimensions too, but we're just working in 2 to kind of learn all the stuff. So this would just be the square root of 4 minus -1 is 5, squared is 25. That'll be 36 when you square it, so you should get root 61. Okay. And if you graphed it, four, 5. Here's P, -1, -1. Here's Q. That's it right there. Okay? Nothing fancy. Questions so far? Okay. Some important concepts. Okay, in the context of vectors, so in vector context, real numbers are called scalars. Okay, in the book, these are just usually lowercase letters, and they typically are italicized. For us, when we write our work or writing things down on paper, we would just remove the vector notation. So if you just see a by itself, that means we're talking about just a regular number. Okay? So it's important that you kind of keep track of the notation, because eventually you do want to be able to follow your work and not get confused between 2 different things here. Second thing is, and this is important, the two vectors are equivalent if and only if they are the same length and have the same direction. Okay. And lastly, vectors can be shifted and they can be positioned at the origin if it makes things easier. So initial point at the origin is what I'm talking about here. So for instance,
I like in this Gonzalez. First of all, I love finding distance and magnitude of vectors. I'm kidding, I feel like this guy. I just like the fact that we have one student who's actually committed to their learning and has separated himself from these heathens over here. Literally, this one goof off. So
no problem.
See you guys.
See ya. And so right here, this picture, we could simply move this P so that it starts at 0, 0. Okay, and then we have what we call component form that comes out of that. Okay, and actually introduce that now. you don't really need to position things at the origin, but it's easier to see, like, if there's a horizontal component and a vertical component, what those would be. Okay, but we can probably just look at this and say how big each component is, right? So if I start at P, how far left would I have to go? And then how far down would you have to go to get to Q? So you'd go 6 to the left and then 5 down. Now let's attach a sign to that. So if we're going left, that's really -6, and if we're going down, that's really -5. So this vector up here, PQ, can also be written in this component form like this. Have you guys seen that before with the bracket notation? Okay. If you haven't, it's pretty simple. This just means horizontal or X component, Y component, and when we start working in 3 dimensions, we'll have a third one, which will be our Z component. Okay? And here you can kind of just see what they are, but the formula is something like this. So if an initial point, yep, thank you. If the initial point is, let's say, x1, y1, and terminal point is x2, y2, the component form of a vector is written with these brackets, and you would just take ending x coordinate minus initial x coordinate, and then do the same with all the other components. And it has to be in that order. Okay? If you don't do it in that order, you still get the same size, but you get a different direction, and that's a huge deal that you don't want to mess around with vectors. Okay? Any questions on that? Okay. Last. Let's talk briefly about zero vectors. You could write 0 with a little vector symbol, and we know that we're talking about a vector that has nothing for every component. So whether it's in 2 dimensions or 3 dimensions or even higher, okay, this means all the same. All right. Quick little theorem, which we don't have to prove because it's kind of intuitive and we should understand what it's saying. 2 vectors are equivalent if and only if, by the way, this is the abbreviation that we typically use for if and only if. It's not actually a word, IFF, but if you see this, it means if and only if. If and only if their components are equal. Two vectors are parallel if they are scalar multiples of each other. Okay, so going back to this one, since I have it already on paper, if I throw a 2 in front of this vector, all that does is double the component lengths, but the vector is still pointing the same direction, we say those are parallel. Okay? I could even have another vector that's identical to this. Let's call it ST. That's another parallel vector because we would just say it's got a scalar coefficient of 1. Does that make sense? Okay. I could even flip this around and put a negative in front. Now we reverse the direction so that this is 6 and then 5. Even though they're pointing opposite directions, they're still along that same line. So we would still consider those parallel. Does that make sense? Okay, we'll deal with that more as it comes up, but just kind of wanted to lay that out there now. Okay. Let's talk about some arithmetic operations. When does this period end, you guys? 34, okay. So let's say we have two vectors. And let's say they're already, written in component form. So let's say V has components V1 and V2. And let's say W has components W1, W2. If I wanted to add or subtract the vectors together, those of you that have taken physics, what do you do? So you separate into components and add them. So yeah, and think, Jerry, you're thinking about length, but and that's what I remember, because I sat in on a physics class years ago, and I think I remember them seeing, I think you even had like a chart or a table, and you would have like X component or whatever, and you'd have all the components written, and then Y component, and then you just add them up, right? Well, on paper, what would I do? My X component would be, yep, V1 plus W1, or I'll put a little minus because subtraction works the same way. Okay, and then the Y component would be V2 plus or minus whatever it is that we're doing, W2. Okay. If I have a scalar times a vector, we kind of hinted at this a little bit already. So if K is just a regular number, all that's going to do is double or triple or whatever it is the components. So this would now be K times V1 times K times V2. Okay. The only thing I'm going to add here is that everything is similar in 3 dimensions. Okay, so if we have a third component, you do exactly the same thing. You just add your components together. If you have a scalar, you would just multiply that third component as well by that scalar. Okay. Now, that's how you do vector operations on paper. You guys in physics probably did a little bit of geometric addition too, right? Where you kind of connected vectors. I think they use the terminology tip to tail. Does that sound familiar? No? Okay. I will. So to add geometrically, so let's say I have vector V that looks like this. And let's say W is another vector that looks like this. And I want to know, what's V plus W look like? Okay. So I always think it's easiest to think about whatever the second vector is, that's the one that you shift. So what you're going to do, since I'm adding W to V, you're going to slide W over so it connects and starts where V ended. Does that make sense? Does that look familiar? Maybe they didn't call it tip to tail, but I'm sure you've seen this, right? And so now here's V, here's W. V plus W would be the very beginning of V to where? The very end of W. Very good. So this new vector, starting at the same initial point as V, but ending where our second vector ends, that is what we call V plus W. This is called, by the way, the resultant force. So anytime you're asked to find a resultant force, what they're really asking you to do is just add all your vectors together. Okay? Subtraction works the same. If I wanted to do V minus W, I'll keep the same orientation that I used here. Here's V. Here's W. Subtracting W is the same thing as adding the opposite. Does that make sense? Just like normal numbers. So when I slide and connect to V, rather than going the same direction, we're just going to reverse it. And now this is negative W. And so V minus W would be same thing from initial point to the end of minus W. Okay. And just real quick, let's say I had a vector at negative 4, 5, 0, and another one W, not at, but with those components. W has components 1, 2, negative 3. Now you should be able to do a multitude of things. So let's say we do negative 3V plus 2W, or magnitude of V minus W. Okay, this is what we mean by arithmetic operations. Okay, so here, negative 3 times V is exactly what it sounds like. You just multiply negative 3 into V. Here you just double W, so 2, 4, negative 6, and then you add. So your final answer is negative 10, 19, negative 6. We're going to run out of time here, we already have, but here you would first subtract the vectors, then find the length. Okay? So real quick, if I did V minus W, that's negative 5, 3, and then 3 again. And so now the length is going to be the square root of, because you guys understand this is x1 minus x2, y1 minus y2, right? So this is what we get in the distance formula when we do it that way. So then you would just square all the terms, add them up. What is that? 1843. Okay? Does that make sense? We'll pick up there in the notes. Over the weekend, I'm going to ask you to kind of finish up the notes, okay? Because we need to